Imagine a universe that began as an infinitesimally small point, a singularity containing all the energy and matter we observe today. In the blink of an eye, this minuscule dot expanded beyond our wildest comprehension. This phenomenon, known as cosmic inflation, unfolded in the very early moments of the universe, shaping everything we see in the cosmos today. Join us on an enlightening journey through time and space as we explore the intricacies of cosmic inflation, what it is, why it matters, and how it transforms our understanding of the universe. To understand cosmic inflation, we must first revisit the Big Bang Theory, which describes the universe's birth around 13.8 billion years ago. In this early stage, the universe existed in an incredibly hot, dense state, filled with fundamental particles and radiation. As it began to cool, these particles formed into atoms, leading to the eventual creation of stars and galaxies. According to inflationary theory, the universe underwent an exponential expansion, growing from subatomic scales to sizes larger than galaxies almost instantaneously. This rapid expansion not only stretched space itself, but also smoothed out any irregularities, creating a remarkably uniform cosmos. The result? The cosmic microwave background radiation, an afterglow from the Big Bang that fills the universe, appearing almost identical in all directions. This isotropy, or uniformity, is crucial to our understanding of the cosmos. Inflation introduces us to the intriguing concept of quantum fluctuations. During this rapid expansion, tiny fluctuations in energy, dictated by the principles of quantum mechanics, were stretched to cosmic scales. These fluctuations seeded the density variations that would eventually give rise to galaxies and large-scale structures. Imagine these fluctuations as the universe's primordial blueprint, imprinted into the very fabric of space-time. The evidence of these fluctuations can be observed today in the cosmic microwave background, providing key insights into the early universe. The concept of cosmic inflation was first proposed in the early 1980s by physicist Alan Guth, who, through his groundbreaking work, laid the groundwork for what would become a transformative theory in cosmology. His insights were built upon by others like Andre Linde and Paul Steinhardt, each contributing to a framework that explains how the universe could expand so dramatically in such a short time. The 1990s and early 2000s saw significant developments, with observational data starting to align with inflationary predictions. The ongoing study of the cosmic microwave background, particularly through missions like NASA's Wilkinson Microwave Anisotropy Probe, WMAP, and the European Space Agency's Planck satellite, has provided critical data supporting inflationary theory. By meticulously mapping the tiny temperature fluctuations in the cosmic microwave background, scientists have confirmed many predictions made by inflationary models, including the existence of large-scale structures that correlate with these fluctuations. Moreover, inflation has profound implications for the large-scale structure of the universe. The patterns we see in the distribution of galaxies and galaxy clusters today can be traced back to the quantum fluctuations that occurred during inflation. These initial density variations, amplified by gravitational forces, laid the groundwork for the gravitational interactions that eventually led to the formation of galaxies, stars, and all the structures we observe in the universe. This understanding unifies cosmology and astrophysics, linking the microscopic quantum realm to the macroscopic universe, illustrating how the infinitesimal and the colossal are intricately connected. The significance of cosmic inflation extends beyond our understanding of the early universe. It raises essential questions about the ultimate fate of our cosmos. Inflation suggests the existence of a multiverse, a vast collection of universes, each governed by its own set of physical laws and constants. This notion challenges our understanding of reality and our place within it. Are we merely one bubble in a vast sea of universes, each born from its own unique inflationary event? The multiverse theory introduces a spectrum of possibilities, inviting us to reconsider fundamental questions about existence and the nature of the cosmos. The multiverse concept is both tantalizing and controversial. Some physicists propose that if inflation can occur in different regions of space, it is plausible that each region could develop its own unique properties. This raises profound questions about the laws of physics as we know them. Are they universal, or are they merely local phenomena? While the multiverse theory is speculative and remains a subject of intense debate, it opens the door to profound philosophical and scientific inquiries about existence. The fine-tuning problem suggests that certain physical constants, such as the gravitational constant or the strength of electromagnetic forces, fall within a narrow range that allows for the formation of stars, planets, and ultimately, life. In a multiverse scenario, where countless universes exist with varying constants, our universe may simply be one of the few that supports life, alleviating the apparent improbability of our existence. This perspective fundamentally alters our understanding of our universe's uniqueness, positioning it within a larger, more complex framework of reality. Looking ahead, advancements in technology are paving the way for groundbreaking discoveries. With next-generation telescopes and observatories, like the James Webb Space Telescope and future gravitational wave detectors, we stand on the brink of unprecedented insights into the universe's structure and origins. These instruments will allow us to peer deeper into the universe than ever before, investigating the earliest galaxies and the cosmic dawn. As we gather more data about the structure and behavior of the universe, we may find additional evidence supporting or refuting inflationary models and their implications. Moreover, new theoretical frameworks are being developed to better understand the mechanisms behind inflation itself. What caused inflation? Was it a specific field, known as the inflaton field, that drove this rapid expansion? As scientists explore these questions, they are not only unraveling the mysteries of our universe's beginnings, but also refining our comprehension of fundamental physics, including quantum gravity and string theory. In conclusion, cosmic inflation is a pivotal concept that revolutionizes our understanding of the early universe and the structures we observe today. It provides a coherent framework for explaining the uniformity of the cosmos, the seeds of galaxies, and even hints at the existence of a multiverse. As we continue to explore the depths of the universe, cosmic inflation serves as a reminder of the mysteries that lie beyond our reach and the boundless curiosity that drives us to seek answers. The journey of understanding our universe is ongoing, and each discovery leads us closer to unraveling the profound truths hidden in the cosmos.